All right, let's talk about localization. So, the first thing we're going to do is we're going to observe that if we have an ideal A in fancy A in our ring capital A, and suppose that its intersection with a multiplicatively closed set S is not empty, then it turns out that considering S inverse A, which have we proved that these are ideals? If we haven't proven that things of this form are an ideal where A is an ideal, then you can just prove it yourself because it's pretty easy. There's no real tricks. But anyways, so if this intersection is non-empty, then it turns out that this ring of fractions is precisely the entire ring, and that's because if this is non-empty, then it contains some element, let's say t. And then if you look at, okay, well, I guess this should be a unit in S inverse, and then the ideal A. Well, so this should be for every single t over 1 is a unit in S inverse A because its inverse is just 1 over t. And we know that 1 over t is going to be in S inverse A because oh, wait a minute. Let me just make sure that I have. This should be just like a really easy one-line proof, and there shouldn't be any tricks going on in here. This is just a very quick observation. Where's the sheet that has this fact on it? S inverse. No. This isn't S inverse A. Because the thing is, t over 1 is an element in S inverse fancy A, the ring, and in fact this is an ideal, so if you multiply by any element in S inverse capital A, then it stays in S inverse fancy A, because that's what an ideal is. So if you take this t over 1, then 1 over t is, well, not necessarily going to be in this ideal S inverse fancy A, but it is in the ring S inverse A because 1 is in A and t is in S. So 1 over t is in there, and if you take t over 1 and multiply by 1 over t, then because you're taking an element of this ideal and multiplying it by an element in the overall ring, then you stay in the ideal. So you multiply them together and you get 1, and so 1 is contained in this ideal. So this ideal is generated by 1, so it's the whole thing. Okay, so that's actually going to be useful for this proposition down here. So if I were to actually plan ahead when I was making this, I would put this observation right before the proposition, but oh well. So yeah, and it turns out, and so this is a useful fact, every ideal in S inverse A is of the form S inverse fancy A, where you take fancy A, just any ideal in A. And so to prove this, you consider any ideal in S inverse A, and you let fancy A be the inverse image under this JS map of that ideal that we started with. So this is everything in A such that A over 1 is in B, because that's what elements in this inverse image look like. So why is this an ideal? At first I thought there wasn't going to be that much in this video, so I decided to write out the details, even though it's pretty easy. Certainly 0 over 1 is in B, because B is an ideal. So 0 is in A, and then if you take two elements in the ideal, then that means that A over 1 and B over 1 are in B, and since B is an ideal, you've got the sum and the multiplication are in the ideal. And so because these are enumerators, these two things are in the ideal as well. So you basically just use the fact that B is an ideal to conclude that A is an ideal. Actually, no, none of this work was necessary. Yes, it was. Maybe. No, it wasn't. Because we know that JS is a ring homomorphism, and we know that inverse images of ideals under ring homomorphisms are ideals. So I didn't have to do all this work. But anyways, whatever. So now we claim that these two ideals are the same thing, and so we just do by inclusion. So take something in B, it's going to be, I guess, why did I introduce X there at all? We don't really use it. So we take something in B, because B is an ideal in S inverse capital A, then it's of the form A over S, where A is in capital A and S is in S. Then, okay, so this is an ideal, so multiplication by anything in the ring stays in there. So in particular, multiplying by S over 1, which we can do because S is in capital A and 1 is in capital S, because that's part of the definition of being closed under multiplication. So this times this just gives you A over 1, so that's in B. But if A over 1 is in B, that means that A is in A. So then A over S is in S inverse A, because this is just fractions where the numerator comes from fancy A and the denominator comes from S. Okay, so we have the inclusion in one direction. So now we want to go the other way, so let's start here and go here. And I don't know why this A looks like a U, whatever. So you take A over S, and you suppose this is an S inverse A. So here, we start by knowing that A is in fancy A. So then what happens? So since A is in fancy A, that means that A over 1 is in B. And so then we can write A over S as 1 over S times A over 1. And because B is an ideal, taking this and multiplying it by an element in the overall ring keeps you in the ideal. So this is in the ideal, but this is equal to this, so A over S is in B. And so then we have this inclusion, and so we have equality. And there you go. Okay, let's talk about localization. And this is probably the most useful part about this whole rings of fractions. Like localization comes up a lot. So suppose we have a proper prime ideal in a ring A, and we take our multiplicatively closed set to be just A, and you exclude all the elements in P. Then, let's see here, why is it closed under multiplication? Or multiplicatively closed? Well, 0 is in P, and so that means that 0 cannot be in S, because we're excluding all the elements in P. And 0 is one of those elements that we're excluding. So 0 is not contained in S. Certainly 1 is contained in S. And why is 1 contained in S? 1 is contained in S that's because this is a proper ideal. So if 1 were in S, that would mean that... No, if 1 were not in S, then that would mean that P contains 1. But since it's an ideal, that would mean that P is equal to the entire ring A, which is not happening here. Okay, and then the other thing, if A and B are not in P, then this is just the definition of a prime ideal. If A and B are not in P, then A times B is not in P as well. So if you've got two elements in here, their product is not in here. So you see there's a really... It's almost like this was kind of built to be used for this, because it's really easy to, this A set minus P works very naturally because you're using the definition of a prime ring very nicely here. Prime ideal. Anyways, so A sub p, so that's not A times p, it's A and then we have a subscript p. We're going to define this to be S inverse A, where S is A set minus p. And this is a localization of A at p. And why do we call it localization? Well, you see the word local there. And what it turns out happening is, remember what a local ring is. A local ring is a ring which has a unique maximal ideal. And turns out performing localization or localizing at a prime ideal gives you a local ring, even if you didn't start out with one. And that's this proposition. A sub p, the localization of A at p, is a local ring, and its unique maximal ideal is just S inverse p, where p is whatever prime ideal we localized at. And so let's prove this. So let's take any ideal b in A sub p. We know by this proposition that b is of the form S inverse fancy A for some ideal fancy A in capital A. And now we use our observation. So note that if A intersect S is non-empty, then B, well, if A intersect S is non-empty, then S inverse A, S inverse fancy A, is equal to S inverse capital A. That's what this observation was. But S inverse fancy A is B. So B equals S inverse A. And so in this scenario, B is not a proper ideal. So if fancy A intersects S non-trivially, then B is not a proper ideal. Contrapositively, if B is a proper ideal, then the intersection of A with S is empty. Okay, but what does that mean? So A intersect A set minus B, because that's what S is empty. But what does that mean if A intersects with the set of things in A which are not contained in P? No, A does not intersect with this set. Well, that means it can't be the case that any element of A lies outside of P, because in that case we would have some element in the intersection. So therefore, A is contained in P. Fancy A is contained in P. Okay, so now what? So if you have fancy A contained in P, then this containment is preserved under taking the ring of fractions, because you're just adding in denominators. So now B, remember, is S inverse fancy A, and now this is contained in S inverse P. So if B is a proper ideal, then B is contained in S inverse P, so S inverse P contains every single proper ideal of S inverse capital A. Okay, and then we're basically done, because if you consider any maximal ideal Q of S inverse capital A, then because it's a proper ideal, we know that it's contained in S inverse P. But this is a maximal ideal, and the only way for it to be contained in another proper ideal is if it's equal to that ideal. So Q is equal to S inverse P. So every single maximal ideal, every single maximal ideal in S inverse capital A is precisely equal to S inverse P. So S inverse P, therefore, is the unique maximal ideal of S inverse A. And yeah, that's about all we have to say, at least for now, about localization. So we have localization, and we get this this kind of neat proof of the fact that that localization gives you local rings. And then the next thing we're going to do is we have this proposition up here that says that ideals in S inverse A are of the form S inverse fancy A, where fancy A comes from the original ring capital A. So you might ask, what happens when we consider prime ideals in this scenario? And we will talk about that in the next video.